Okay, good. Well, thank you very much, and thank you to both Vittoria and Laura for organizing this and inviting me. It's very nice to be in Vienna with this very nice weather, and of course also thank to the center here that permits and to the university, and also to the fact that they really put a lot of money and resources in providing such a center to organize this kind of events, which is very nice. Okay, so this is the last talk before lunch, so there should be a good motivation for you to attend until the end, and the good motivation can be that I will literally tell you how you can get a paper published in Nature Communication as a co-author, which will be cited a lot. So by the end of the talk, you will know how to do that if you want to put a little bit of effort. Okay? So this talk, many people in the audience have been involved with the Andy Challenge, so I will maybe skip on some small details, and you are free to ask me during the talk. I don't mind if you interrupt me. So the Andy Challenge is about anomalous diffusion. So even to this audience, I want to present what is normal diffusion. You know, you have these particles that are diffusing, and there is a mean square displacement that is linear in time. Nothing new. We've seen basically this in every single talk until now. What is interesting is that there is also anomalous diffusion, and also here it's very nice that I don't really need to explain what it is the fact that the slope is different from 1, and why it's important and how it comes about and so on. Basically, most of the talks until now have shown cases in which interactions, crowdedness, and flows of energy and so on can lead to various kinds of anomalous diffusion. Okay. So given this, we can see this kind of anomalous diffusion in every system. Many of these have already been shown in the previous talks during this workshop. But, and of course, we can also mention the fact that the study of, well, essentially Betzig, Hell, and Murnay got the Nobel Prize, not for studying anomalous diffusion, but for providing tools that now have really opened the door to the study of anomalous diffusion in cells and in biological systems, thanks to super resolution microscopy with very high frequency. But let's keep in mind that you can have anomalous diffusion also on much larger scale. For example, if you look at how animals forage, you will see some anomalous diffusion behaviors, but you can also reproduce it on the atomic level using some kind of atomic potential and seeing how the atoms jump between these potentials. Okay, so anomalous diffusion, as I just briefly mentioned, goes back to particle tracking, and I'm not going to explain particle tracking to this audience. They're very nice. The chair of this session already showed how you might even not need to do particle tracking, and I like that very much because it's true. You can get a lot of information even if you don't track the particle, but any particle tracking effort will start from taking a video of particles, then typically you will essentially threshold it and finally reconstruct trajectories if you have enough temporal resolution, obviously, to actually follow the single trajectories. And if you do this, essentially you can measure the Brownian motion of the particle and double check that per-n is still right. So in fact, per-n, which should appear, I guess, in every single talk of this workshop, so I dutifully have the manually digital tracking of particles made by per-n, and well, he showed that that was really the first, I would say the first example of a quantitative microscopy analysis where really someone used the microscopic data to quantify the properties of a system to the point that he demonstrated the existence of atoms, essentially. But this then was followed by the development of new techniques, first through the development of electronic and computer-based techniques to analyze the motion of particles. This is all work that went on from the 50s to the 90s. A very big outcome of that work is flow cytometry. So if any of you has done any blood analysis, that goes to a flow cytometers, which is an offspring of this kind of analysis. And very recently, there has been a lot of interest also in applying deep learning methods. So within the machine learning revolution, the AI revolution in the last 10 years, there have been lots of tools from deep learning that have been applied to particle tracking and so on. and we also contributed some to this through a package, a software package called DeepTrack that permits to do particle tracking, more in general, quantitative macroscopy. This gives you an idea of the timeline of how the study of the tracking of particles has evolved over time. One thing that I found very interesting, I like very much the counting approach of yesterday again, because what is beautiful there is, well, essentially what was said yesterday, that you don't really need to track the particle in each frame, so to find which particle is which in the next frame. That's very powerful, of course, because this means that you don't really need to identify which particle is which, but also you can skip the, this opens new possibilities. You can go to very crowded environment, to environments where there is blinking, where the particle disappears in some frame and so on. So we have also done some work in that direction, which I will not present, but there, in that case, what we did was to use a graph convolutional neural network to analyze particles prescinding from reconstructing explicit trajectory, which actually permits to find out properties of a global properties of the system without actually having to reconstruct the trajectories. Anyway, so going back to anomalous diffusion has been observed, and this is thanks to this particle tracking. And if you go back, the first example of particle tracking with microscopic system with molecules goes back in the 1980s, when people start playing with fluorophores, quantum dots, and all these systems. And what they observed was essentially that, well, they started observing something strange, and one interesting thing is that people started observing this anomalous diffusion. And what is very interesting to notice here is that at the time, the idea that there could be anomalous diffusion was very, very surprising, to the point that if you read the title of this paper, they didn't just say subdiffusion, but they said anomalous subdiffusion. So they really reinforced the idea that they were not expecting such a behavior in a system. And this is not a typo, so it doesn't appear only in that paper, but it's something that really was used quite broadly, like when these things started being observed. So this gives an idea how surprising it was for the people that start observing something that was deviating from Einstein dogma in molecular systems. Okay, so a lot of study followed up, studying anomalous diffusion in general. And one thing that happened around maybe 5 years ago is that many people started combining. As I mentioned, there has been this AI revolution. There was a lot of interest in anomalous diffusion. People start combining the two things. And what happened is that in the span of a few months, there were like 6, 7 different papers that came up from different groups. So these are all from different groups spread around the world that all thought, why don't we apply some machine learning methods, mostly deep learning, but not only. There was also, for example, random forests. Why don't we apply these methods to study anomalous diffusion? And this happened all at once. And it was very interesting. Just to give you an idea how interesting it was, people could extract ensemble properties that are typically considered ensemble properties, like whether a system is ergodic or not, from a single trajectory, which again is something that you wouldn't expect a priori. And this wealth of developments applying AI to the study of diffusion and anomalous diffusion led, essentially led Carlo Manzo, not me, but Carlo Manzo, to think about the possibility of creating a challenge for the community to see which methods were the best. So, these challenges, this is a screenshot from Kaggle, which is one of the major, I guess all of you know what it is. So here there are challenges. So if you're a company and you want some problem solved by the best engineers around the world and you don't want to pay them, you open a challenge in Kaggle, give maybe $100,000 prize, and you will get lots of people to compete for that prize. Most of the time, these people will make their software freely available. So you give $100,000, you get best results. So you will see a lot of companies put their challenges here. But this, apart from that, this aspect, challenges are very good because they really permit to construct a community around different themes. And this has been going on for many years in the fields related to microscopy. So here you see a lot of papers that were published in different Nature journals about basically comparing, for example, this is a very, very famous one in which There is a comparison of different tracking methods for particles and a variation of this. So there are continuous challenges coming up, for example, to find out what is the best segmentation strategy, what is the best, basically almost anything you can imagine, because this has a direct relevance for practitioners of medicine and biology. Okay, so that's where we stand, and we decided, by we I mean Carlo Manzo decided that he should organize a challenge. And so once you want to organize a challenge, you have to start thinking of many things. I mean, it sounds easy, let's make a challenge, but it's not so easy, because you have to start thinking of a lot of things. Start thinking about, well, first of all, you need some data sets for which you know the ground truth. How are you going to tell how the participants score if you don't know what is the ground truth? Then you have to decide where to host the challenge. You can do it on Kaggle in principle, but Kaggle requires you to put a monetary price. Now, any of you who got grants, typically you cannot use your grant money to create a prize, because it's like giving money away. Even though it will be very valuable for science, you can actually not do that. So Kaggle was out of the question. You need to decide which community to address. You need to decide how you are going to evaluate the challenge, because different scoring systems will give different winners of the challenge, obviously. And of course, you have to eventually decide how you are going to publish these results of the challenge, because, you know, at the end of the day, scientists are really motivated by publications, because that's what then drives everything else. I mean, it's a way that you show that you are productive, but also a way to then tell the grant agency that you should get more money to get more publications. So you have to think of all these things. And luckily, I was not involved in this first phase, so Carlo had to do all the thinking, together with other people. I will mention all the people involved soon. So there are lots and lots of questions. I mentioned most of the questions that come up in all of these points. So we really have to think about how we get the data, which platform to use, which community are we going to address, how we are going to evaluate, and what's the final publication outcome of this challenge. How do we know? Because, you know, you have to run the challenge first and convince people to be in the challenge, and you cannot really tell them, look, you are going to publish it. You don't really know what's going to happen at the end. Okay, so we went through all of this, and the first step was deciding which models of Brownian anomalous diffusion to consider. These are the ones that, these are the ones that we ended up with, and you see these are the most common ones. They're not all of them. You can think of new models. But anyway, Levy-Walks, scale Brownian motion, fractional Brownian motion, continuous time random walk, and ATTM, which is anneal transient time motion. These are the 5 models that were used for the challenge. And then there were, what task are we going to make in the challenge? So that, okay, keep in mind that the people involved in the organization of this first challenge were physicists. So a physicist, mostly physicists, even physics-oriented biologists. So when you think of a physicist comes up with a question about anomalous diffusion, the first thing they think about is, what is the underlying model? That's nice mathematical physics question. Second question will be, what is the anomalous exponent? What is the exact value of alpha? Is it, alpha here refers to the anomalous exponents. Just to be clear, this has nothing to do with the alpha that defines Ito Stratonovich. It's a different alpha, even though you use alpha for both of them. So what is the exact value? Is it 1 or 1.01? That makes a difference for a physicist. So what is the model? What is the underlying model? And of course, if you have a trajectory that is long, are there change points? Is the trajectory going to switch between different behaviors? And what are these behaviors? When does it switch? These are the questions that interest physicists. I insist on that because it becomes relevant later. And of course, for each one of these, we have to define some quantifiers, and we use the mean absolute error, F1 score, and some kind of weighted ranking in the case of the. Doesn't really matter too much what we chose here. They make sense within this task. We could have chosen something slightly different, but probably would not have changed so much the conclusions. Okay, and then we also decided to do this in 3 dimensions, so 1D, 2D, and 3D, because this is representative of a biologically relevant situation, going from single file diffusion to membrane, diffusion in membranes, and diffusion in a 3-dimensional space like cytoplasm. Okay, so you see that we have 3 tasks and 3 different conditions, so we have a total of 9 tasks for this challenge 1. Okay, so that's what we did. And at that point, one thing that I didn't say explicitly, we needed a ground truth, therefore we decided to simulate the data that we give to the challenge participant. Why do we simulate them? For the obvious reason that then we know exactly what they are. And the participant have had access to the simulation code, so they could simulate more data for themselves. But the data set, there was nothing secret. All the code was completely open access, is completely open access, and includes the data sets, the simulation of the data sets, everything. The only thing that was obviously not open access was the test data set that we used for the challenge that was kept secret, even from the organizers. Okay, so at this point, we also wanted to know, okay, we are going to do all this challenge on simulated data, but how relevant will this be for experimental data? So what we decided to do was to inject a few experimental data in the evaluation data set that we were going to use for the challenge. And in this injection, we added them without telling the participants, but we didn't score the experimental data. So when the participants were trying to classify trajectories, they were also trying to classify trajectories from these 4 different experimental situations, which you see include the mRNA, different kinds of system. But we were not using them for the scoring, but there to give us a result so that we can then evaluate how well they were doing on the experimental data. Okay, so let's see what came out of this. Actually, no, let's see first what was the story. So as I said, the first idea came from Carlo Manzo. It started in 2019, which is a year that might ring a bell. And then there was a lot of work of organization. So Carlo worked with the people in Maciek's Levenstein group, in particular Gorka and Miguel Angel Garcia Mar. And after that, we joined, Ralph and myself, a bit later. I hope that the timeline is correct. Because they proposed it to, at least to me, they proposed me this, and I said, yes, of course I want to participate, since a very nice activity. And then it started the actual work, where we had weekly meetings to sort out all the software, all the you had to put up a website, you had to choose check the Coda. We use CodaLab at the end, which is an alternative to Kaggle, which is developed in France, and we had to actually be sure that it was working. So then we had to put up all the software that needed to be released for the participant in the challenge. And at the end, we managed to kick off the challenge on the 1st of March 2020. Does he remember anything, this date? This was extremely fortunate for us. So this was a very good time to start the challenge, because obviously when we started the challenge, all theoretical physicists and mathematicians were locked in their houses with nothing to do, essentially. So at that point, they had really 6 months in which they could really work out their methods to make them work as well as possible. And then we had a second phase. So in this second phase was really challenge phase, where we made a ranking, and the top participants were admitted to the final phase, which was 1 week, where we made the final ranking. And after that, there was an announcement of the winners. Then again, there was a lot of work here. You see, 1 year to write a wrap-up paper, and then to have a workshop, which came out in ICFO 1 year later, again, also because of pandemics-related restrictions, and also a special issue. So there was a wrap-up paper, also a special issue where all participants could write in detail their methods so that all this knowledge was not lost. And in fact, most of the participants did that, so there is a huge amount of knowledge that is concentrated in that. Okay, so this is the list of participants. Probably some of you will recognize themselves in that list. Well, you know it already. I will not go through the list, otherwise we don't have time. I will just go through the conclusion of the task. So as we said before, we had 3 different tasks with 3 different dimensions. So the first task was inference of the anomalous diffusion exponent. And I will focus on the 1D case, because the results are quite similar qualitatively. And here you see the different participants, and this is the mean absolute error. So you do better if you have a lower mean absolute error. So you want this bar to be as small as possible. And the interesting thing here is that the top methods are all methods that use deep learning or machine learning, not only deep learning. So while the more analytical based method actually came on the bottom. So this practically, what does this mean? Well, this is, by the way, what you will get using this, just taking the time average mean square displacement. So this means that most methods do better than just using the time average mean square displacement. So there is a lot of gain from using these methods. I mean, use that as baseline. But what is very interesting is that you have a much more to gain if you actually use deep learning methods. Of course, this, a thing that I might mention here, we use trajectories that were relatively short and noisy. If you have a very long trajectory, then this advantage decreases very, very quickly. So just, so let's see here. These are the different models. I don't really want to go to the models, but here, as a length of trajectory, you see that all methods obviously get better as the trajectory gets longer, as you would expect, but also all of them retain some advantage over the mean square displacement. So there is an advantage up to 1,000 steps. Of course, if you have a 1 million step trajectory, probably this advantage will not be so big. We're still speaking of relatively small trajectory, but comparable with what you might have in an experiment. And obviously, also they improve as the signal-to-noise ratio increases. Again, we are speaking of signal-to-noise ratios between 1 and 10, which are not very high. Obviously, if you have 100 signal-to-noise ratio, you might have a slightly different result. Okay, so then let's move to the second task, which was classification of the underlying model. And here, again, the top methods are all based on machine learning. The bottom methods are the one based on statistical inference. And here you see how they do as a function of the anomalous exponent. Not too surprisingly, they get worse around alpha equal 1, which means when you have when they are diffusing, just normally diffusing, which is not too surprising because all methods should converge. Actually, you might even think that it's surprising that they can distinguish the different models at alpha equal 1. But keep in mind that alpha equal 1 means that your model will have the mean square displacement with slope 1 at long times. But there are still microscopic differences in the steps that your system takes. And obviously, this method can pick up on those, which is nice to see. Again, keep in mind that there was a lot of noise on top of the trajectory, so it was not so trivial to pick up on that. So that is reasonable. The drop in 0 is simply because the trajectory is effectively smaller. Again, they improve as a function of the number of time steps, not surprisingly. They also improve as a function of the signal-to-noise ratio. Again, not surprisingly. And you see that they have a pretty good discriminative power. So this is a confusion matrix. And you see that most of the entries are on the diagonal, which means that they are correctly classified. This is the best method in this set. Maybe one thing you want to notice also is that all the top methods are very, very close to each other. So it's not that we had one method that was so much better than everything else. This is actually good from our point of view because this means that all these methods that reach the top really managed to extract all the information that they could extract from the data, and this amount of information is similar for all cases. Okay, and finally, there was this one case in which you have a jump, an example of segmentation between different trajectory that switches between two different behaviors. And here we had only 3 participants, so the conclusions are not so strong. But what is nice is that they all do much better than a random prediction. So it means that you can find change points, and it should be quite robust against the kind of method that you use. Many more participants did this in the special issue because the special issue came out after and they managed to do much better. Okay, so here there is a lot of discussion, which I will skip. And if you want to play with it, there is an interactive tool where you can upload your own data and compare yourself against the participants. I'm not going to go into the details of this because I want to very, very briefly discuss the results on the experimental data. And here it's very, very interesting because the nice thing is that these were pre-published experimental data. So we had someone that had already studied them and told us what they are supposed to be. And here you see that what is very nice to see is that in this case, all the top methods do very, very well in agreement with what the authors of the paper suggested, and better than the mean-squared displacement. And in the classification of this data, they do worse. So all the methods agree that this is ATTM, but there is one important thing. ATTM was published in 2015, I think, by Maciek Levenstein and co-workers. So it didn't really exist in 2006. So, you know, the classification as a continuous time under work is not unreasonable if you exclude the ATTM. So even here, it's not a bad result, this one. The fact that, but what is very nice here is that they all agree. And these are different groups that develop the methods. So it really means that there is something. You can do the same for this other work, which I'm going to go very fast. But here you see that now there is very, very good agreement both in alpha and in the result. There is also good agreement in this one on the membranes, again. And finally, there is also good agreement in this atomic potential. Here, it's much broader everything because this trajectory is extremely small, like 10 steps, 15 steps. And you see that, but even in this case, you see that the discriminatory power of this method is pretty good. Okay, in the last maybe 1 minute, 2 minutes, I think. The conclusions are very, very quick because I already said everything. So the main conclusion are there is a lot of information that can be extracted that goes beyond the mean-square displacement. So it's worthy developing these methods. And what is very nice is that all these methods converge towards very similar results that worked similarly also on experimental data for which we had not created the ground truth. And they all converge to very, very similar results, which probably is a sign that we're really extracting all the information that is there. So you cannot really also, you know, you can use any of the methods that are on the top and you will do more or less equally well. Because probably if you change slightly the scoring function, we would have gotten slightly different results for the top 5 methods, obviously. Okay. And this was work, as I said, the organizers were originally Carlo Manzo and Gorka Munoz, Gil, obviously, who is, by the way, now in Austria, in Innsbruck. And then a lot of people joined organizing, these people here, some of them in the room. And all of these people here are all people that participated to this first Andy challenge. And this is the special issue where there are lots of papers that really go into the details of each of these methods. Okay, and now it's where I come to the promise I made you, which is that if you listen to me and do something for us and for yourself, you can have a paper in Nature Communication that will be very well cited. So now, after this challenge, we decided to go, well, we didn't really decide, but we started discussing with biologists, and biologists told us, look, we don't really care about what you did. We don't care. That's why I was saying, there was a group of physicists, and they told us essentially we don't really care about the anomalous diffusion exponent. We don't really care too much about the underlying model. What we care about are other things. And therefore, we decided to create a second challenge addressing the issues that biologists care about. The team that organized is very, very similar. The main addition is Diego, that also is also on the core organizing committee, but the rest is more or less very similar. And this paper is now a registered report in Nature Communication. So we made everything upside down this time. So first we prepare the structure of the challenge. We prepare a paper about the structure of the challenge. We submit it to Nature Communication, and they got it approved by the referees, which means that now it will be published unless we do something extremely bad, and whichever is the result of the challenge. So we don't really have to, you know, this idea of registered report was created mainly for clinical studies, so that you can have a clinical study that is accepted in principle before it's actually run, so that the design is good, everything is good, and we don't care if you get that the drug works or not. If it doesn't work, you will still publish and it will be in the record. So that's the idea where the concept of registered report happened. So this paper is a registered report in Nature Communication, which means that if you participate in the challenge, you will be part of this paper, as long as you are in the top. I mean, now not everyone who participates like the first time will be there, but the top is quite quite flexible. So, I mean, as long as you do it well, it will be fine. So what is the challenge now? The challenge will be this one. So we have, first of all, we focus on two-dimensional systems, and we study two things. So you see, you can have a video, and you can extract a trajectory. Again, very nice, very resonates very well with the things we have already seen here. And we could analyze the video, or we could analyze the trajectory extracted from the videos. And we can, and in each case, we can study the ensemble. So what are the ensemble properties of the system, or we can study the property of a single trajectory. So we have at the end 4 different tasks, which will permit us to answer questions like, is it actually worthy going from the video to the trajectory before doing an analysis, or you can just study the original video? That's one of the questions that we should be able to answer thanks to this challenge. But then also the task, the kind of models that we have are the ones that really biologists seem to care about much more than about the details of the model, mathematical models and anomalous exponent. So we have these 5 different states of a system, models. One is just a single state model, so like a fractional Brownian motion if you wish. Another is a multi-state where you have a switch between 2 different modalities. Another is where a system of dimerization, where 2 particles can come together and sometimes attach, diffuse together, and then separate again. A model where you have compartments, like membraneless compartments, if you want to think in biology terms. And finally, a model where you can have some quenched trapping, so that you have some sites where the particle can get stuck and trapped there. Okay, and what we did was to make these simulations and then extract this, and then essentially, as a challenge participant, you will get the videos and the trajectory, or the trajectories, and use that for trying to answer what are the properties of this system. So what models are under there, and so on and so forth. Okay, so what's the next step? So now we have this registered, the challenge open on the 1st of December, but now we are in the first phase where we are just attracting people that want to participate, which lasts until the end of this month. So you're still perfectly on time to have a look at it and start it. And then there will be a second phase, which will be until the end of July, end of June. And no, end of June, yes. And this phase is where you start competing with each other for real, then a final phase for the final ranking, and after that there will be an announcement of the winners in July. The wrap-up paper will be based on these results, and now will be written very quickly because we basically already written everything apart from the results. And we will have a workshop probably in ICFO and probably in December 24. And I'm done. I'm literally done. How much time did I take? Sorry. Oh, you should have interrupted me. Okay, that's it.